first presentation is Alzheimer's Disease Drug Discovery Center Data Sharing Platform, presented live by Rob Quick. So take it away, please, Rob.
I need to unmute myself, I guess. Can you hear me okay?
There, we can hear you just fine, yep.
Okay, great. And you're seeing my slide and not my notes, hopefully.
Correct.
So good afternoon. My name is Rob. I'm going to talk to you about the Alzheimer's Disease Drug Discovery Center and the open access data sharing portal that is part of that. But before I start, I hope I learned something from yesterday's plenary, and I want to give kind of a big overview statement about what I think the Alzheimer's Disease Drug Discovery Center and this OADS portion of it really means. So I've provided a lot of effort in the last almost 20 years to various different academic research computing projects. Some of that work was with projects like LIGO or the Atlas of CMS detectors at CERN. And they've led to massively important discoveries and even some Nobel Prizes there. However, a few of the projects that I've worked on really have the potential for the immediate real-world impact, like the Gateway project that the Cyber Infrastructure Integration Research Center is working on now with the IU School of Medicine for sharing drug discovery research for Alzheimer's disease. So getting into this. A note before we start about Alzheimer's disease, if this is something people are already familiar with, please bear with me. But I thought I should say something about the disease. And I saw there were about 20 people in the room. Statistics say that about 1 in 10 adults over 65 will have some form of Alzheimer's and dementia, about 1 in 3 adults over 85. So if there's 20 people in the room, that means 2 of them will likely suffer from Alzheimer's by 65, and then 6 or 7 of the 20 people in the room by the time they reach 85. So now there's some, I think assume this is an educated group, and there is some decrease in risk with levels of education for various reasons. However, the AD, and I'll say AD for Alzheimer's disease quite a bit, but the Alzheimer's disease landscape is complicated, and there are no known biomarkers for early detection, and there's also a high failure rate in drug discovery programs that have been attempted so far. In fact, just down the road, some of my neighbors work for Lilly, and the drug discovery program for AD has been discontinued there, or at least the portion that my neighbors have worked for. So, and as everyone can picture, if they haven't known someone with Alzheimer's disease, it's really a heartbreaking disease. It destroys memory skills, it destroys thinking skills, and eventually the ability to carry out daily activities. So let me talk about 83C. My goal in submitting this paper was really to put this project together in my own head, more than it was to share it with a larger audience. But one way to put a project together in your own head is to prepare to talk about it with a larger audience. So let's talk about the primary goals of the project overall. It's a 5-year project funded by the National Initiative on Health, or NIH, and the award number is on the first slide if anybody's interested in that. We're starting year number 2 of 5 years, and the goals are to identify promising AD drugs and create a portfolio of targets for further research, to allow medicinal chemists and structural biologists and other researchers to research the property of these drugs and validate the targets, in the end providing something we call a target enablement package that can move on for additional testing to preclinical or clinical phases. Third, to identify molecules that have a pharmacological or biological activity likely to be therapeutically useful. These are called lead molecules. And then to share the findings openly. And really that last step is where the CIRC at Indiana University comes into play. So sharing this data openly, along with facilitating access to computational research, is what we're trying to do here. And this is done in something, and I don't know if you can see my cursor, called the OADS, or the Open Access Data System. Most data, though not all of it, will come from open source repositories, things like Kemble or PubChem or the AD Knowledge Portal. And this will be analyzed by chemists, biologists, and other informatics researchers. Once that research is completed, it'll be pushed to these target enablement packages that I mentioned. And the ADS itself will then have both an interface for these target enablement packages to be pulled from, but it'll also push to other AD research portals. These things are the Treat AD portal, the AMP AD portal, and synapse.org. So it'll not only serve up the results, it will push them to other important databases for consumption there. And really, I'll go back to that picture. The CIRC is working here in the BCB area along with the Open Access Data System in developing that. And BCB is the Bioinformatics and Computational Biology core. There's stuff that is not necessarily done as the core research by the chemists and biologists and collaborative researchers that is outside the traditional drug design or drug discovery process. So the Bioinformatics and Computational Biology core has three main goals: designing and running the infrastructure for the AD3C project. And I should say cyber infrastructure there, not necessarily the other infrastructure. Looking for new methods for predicting and prioritizing these target drugs, and finally providing bioinformatics support and, as it turns out, other general IT support to the project. So the components as I saw them, and sitting back and just kind of thinking about what the main components were of the portal and the project as we were trying to develop them, are one, software that either a researcher contributed or is open source, needs to be brought into the portal. The data from both local and publicly hosted data sets, the computational resources for running analysis and services that we're running currently on Exceed, and then some IU resources, but also have our persistent services hosted on Jetstream. And then a UI for the BCB portal itself, which we're using the Apache Ariavada middleware stack, and a repository where interested researchers can pull the data outputs, and then a handful of public repositories we push the data outputs to. And so these are kind of the core structural or architectural components. Let's see. And so we got that down, and I got that pretty straight in my head, and I think we had some ideas as what to do, but wait, the group that was mostly made up of the medicinal chemists, but also the structural biology guys, came and said, well, there's this drug discovery environment called the CDD Vault that we would really like to use as our work area for doing common drug discovery type research. And this CDD Vault is a commercial project, a commercially provided cloud-hosted environment. And it really is a collaborative environment for the researchers to do those first steps of both pulling the open source data and doing some initial analysis. So we kind of had to take a step back here again, and it wasn't, this BCB portal wasn't as long as are covering all the researchers here. It was only covering a portion of them, but we still needed to get all the stuff from both the BCB portal and the vendor database into the OADS. And so we took a step back with these additional complexities and said, you know, if we're looking at a standard computational gateway, we're looking at a data sharing portal. Now we're talking about integrating external commercially hosted cloud services. Let's take a step back and really dig into a data management plan. And this is what a lot of the work in year one of the project went into, was really trying to say, you know, what is the data flow? Where does the data come from? What are the various steps, and where will it be housed at various steps along the process? And where will it in the end be delivered to? So we stepped back, did a data management plan, and this data management plan It provided a lot of things, but really what it provided was a picture of the data flow through the project. So we provided this data management plan. It defined all the things that data management plans define, the roles and responsibilities, onboarding, offboarding, the sponsor requirements, the sharing requirements, quality assurance, quality control, and then the physical, where would it be stored, how long would it be stored, how would that storage be organized, and also brought in the intellectual property rights lawyers, which, as everybody knows, once you get the institutional lawyers involved, it goes to another level of complexity. And while I like to think the motivation was really understanding the data, this was also necessary to purchase the externally hosted software, especially something that has potential for intellectual property to be involved. We really needed to understand this not only for the architecturing of future components, but also so we could feel safe that the data was flowing through these externally hosted cloud services in a way that was secure and would not be lost. So, and I think the DMP was critical not only for that purchase process, but also it's going to be critical as we design the open access data system. So I'll go to takeaways, and it looks like I'm right on time here, so that's pretty good. So the project became much more complex with the addition of commercial components. There was a lot of general IT support the group needed, not only gateway development. So we went in thinking this was a gateway development project. It turned out being a let's help these Alzheimer's researchers, many of who were moving from commercial to academic environments for the first time, work through their IT issues. And so while some of this fit into the standard computational gateway, I'm pretty positive that we'll have to have extensions to what is a traditional gateway for the data sharing components, or the external data sharing components. And we're all early in the process, as I said, year 1 of 5, and I feel that complexity may continue to grow. In fact, there's a second commercial project that is not externally hosted, that is locally hosted. I've installed that on Jetstream, and we're running local services now along with the externally hosted services, and these all have to be integrated and talk to each other. I want to say, if there's one takeaway from this, start the DMP early in the process. It's critical to the design, especially if you're doing something like data sharing and integrating with external services. And possibly, okay, so I said I had one takeaway from this, the DMP, two takeaways from this. The drug discovery research, I think, is super critical to the future of Alzheimer's. And I think what we learn here can also be put towards drug discovery for other diseases. I know there are similar type portals for many other diseases that are doing drug discovery, and we hope that the lessons that we learn about Alzheimer's are transferable to other areas where drug discovery is important to the research that's being done. And I'll stop there.
Great, thanks, Rob. Do want to encourage anyone, if you have any questions, drop them in the chat, or you can perhaps raise your hand. Rob, I'll start with, I don't know if you got a chance to see the plenary a few hours ago, but it was all about interoperability of gateways. And I mean, as you were going through your presentation, I was just amazed at the number of things that you were having to interoperate with in terms of, you know, not just different cyber infrastructure stuff. You mentioned Jetstream and on-prem stuff, but you said there's all these databases, there's all these different things. So I don't know if there's more that you want to talk about along that line. If you got to see it, maybe there's some insights you have from the plenary. Just want to kind of tee that up as a question.
Yeah, so interoperability is a great question, and interoperability, especially in the data realms, is something that's being tackled by many groups. In fact, I have a small NSF grant that looks at general data interoperability. It looks a little less at other interoperability through systems and such, but so I think that the data interoperability, especially in a data-heavy project like this, is going to be super important. How do people get not only the data, but all the associated metadata and the provenance information about what's happening and what they're pulling from this data portal? So I think that's a super important question, and I think that interoperability is going to be one of the major questions of the next 5 to 10 years.
Okay. I see a question in chat that it's kind of an amusing question, but I think we know the answer to it. Did you DMP yourself, or did your funder require it?
So the funder and both NIH and NSF require a data management plan. The data management plan you submit with a proposal is usually not sufficient to really have for a data management plan, especially when you're moving data externally. So yes, there was a data management plan. Was it sufficient to understand and really operate moving through 5 years? It wasn't. And in fact, the DMP should be a living document and change as the project evolves. So it's hard to submit a DMP up front and say that that's encompassing of everything that you're going to do.
Okay, and we'll get one more quick question in. Will the project handle PII or HIPAA? Will be HIPAA compliant?
So no, there's nothing, the only restriction on the data, so it's not critically restricted data, so there's no personal information in there. There is intellectual property information, as I mentioned during the thing. So there was some restriction in that we can't move the target enablement package to be public until it is properly approved by the intellectual property and patent lawyers. So there's a restriction in the data, but not a restriction in that we're using probably 90% of what we'll be using is actually public data to begin with, right? So it's coming from places like Kemble and the PubMed and such. So there's nothing there that will identify people. So there's no need at this point to be HIPAA compliant. There is a need to be careful with the data because it does have legal ramifications in IP and patent areas.
Okay. Well, thank you, Rob. Obviously, please stay because we're going to have a general Q&A here at the end. But let's move on to our second presentation. It's Accelerating Neuroimaging Research with Brainforge. It's presented, it's actually a pre-recorded presentation by Eric Werner, but I see Eric is on as well, so he'll hopefully be available for questions at the end. And Mike, do you want to go ahead and play that?
Hello, my name is Eric Werner, and I am from the Center for Translational Research in Neuroimaging and Data Science, also known as TRENDS, here in Atlanta, Georgia. I'm here to introduce Brainforge today, a web-based platform for neuroimaging research. Brainforge is a cloud-enabled, web-based analysis platform for neuroimaging research. Brainforge allows you to archive data from your study, set up the analyses you want to run, and then process data across multiple modalities. When your results are finished, you can share them with other collaborators on the web. The reason we created Brainforge was for multiple reasons. They were divided into 4 main categories: software issues, reproducibility issues, computational resource issues, and data sharing issues. Now, the first is software issues. Neuroimaging pipelines are quite complicated, and they require lots of advanced software. Now, it's difficult for a beginning grad student or even a seasoned neuroimaging researcher to set up some of these programs sometimes, especially on an environment controlled that they don't have administrative access on. It's also difficult because not a lot of neuroimaging researchers are excellent programmers either, so they don't create code that's maintainable. Now this leads into reproducibility issues. Even if someone can write great code to do a study that does what they need, a lot of times it's not maintainable. There will be hard-coded paths, or it'll be difficult to read, or there will be aspects about the environment that are not encoded and not saved anywhere in the text. For instance, the version of software that the person ran or the operating system that they ran on. Now, this is difficult when maybe a year or 2 down the road, someone tries to replicate their analyses and is unable to. Next are computational resource issues. Now, neuroimaging data is quite vast. It could be maybe one terabyte for a study of 100 subjects just in the original data, and then maybe 10 times that in derived data once you have processed the data. Now, just storing the data is difficult, but also running it can be hard for many people. When you move up to thousands of subjects, which are needed for an effect size to capture small effect sizes, many people do not have the resources to run all the processing that is needed. There are queues like Exceed, in which you can run data for free, but this is not easily. But the queues are very long, so it's not easy for researchers to do their research on time. Furthermore, there's data sharing issues. Once someone has written their code and run their analysis, everything often stays on the file system or the hard drive on which the analysis was originally run. Now, data sharing, then if someone wants to find this analysis, they have to have access to the local file system. Now, this is very hard when you want to share your results with other researchers. On Brainforge, we tackle all of these issues. Our software uses pipelines that have been run and tested in many published studies by Dr. Calhoun and many other researchers at Trends. And these are all encapsulated inside of Docker and Singularity containers, which use all of the encapsulate all of the operating system and software libraries and scripts needed to run the analyses that researchers actually have to run. So it saves a great deal of time for researchers who want to pre-process and analyze their subjects. Additionally, the use of Docker containers lends itself to much better reproducibility. Containerization means that you have the exact software library and the operating system for all within one file, the Docker container. And then if someone else wants to run it, they can just take that container and run it on their own files. Furthermore, we keep track of the provenance, the parameters used, and we store in the database the file and all of the associated metadata that was used for an analysis. At Trends, we have great computational resources. We utilize the HPC, the High Performance Computing Cluster at GSU, and can tap into Amazon Web Services to run analyses. Furthermore, with our web interface, we're able to easily share results with other researchers outside of our own lab. Here's an overview of our architecture. You can see on the left is the Coins architecture. Coins is another product, another study management product that Trends has created about 10 years ago and is still using today. We have Brainforge integrates with Trends and pulls data collected by Coins so that the data can be processed inside of Brainforge. Brainforge has both separate front-end and back-end code bases and uses a Postgres database. We use Slurm as the executor on our HPC to run many analyses at once. And here's an overview of the computational resources we have at Trends. We have 49 servers, over almost 2,500 cores, almost 40 terabytes of memory among all of these servers, and 60 graphical processing units. We also have 1.5 petabytes of network storage and can tap into unlimited AWS resources. Now here's an overview of the analyses that we can run on Brainforge. We can run analyses in neuroimaging pre-processing. We can run linear models using the statistical parametric mapping toolbox. We can run analyses in GIFT, the Group ICA for fMRI toolbox, which is another product of the Calhoun lab. Furthermore, we can do statistical modeling with regression and classification. Here's a screenshot of the Brainforge UI. This is the pre-processing summary. Brainforge allows you to select within a study, you'll have many subjects. Then each subject will have one or more sessions, and which is just a period of time that someone went to go get scanned in an MRI scanner. And then within those sessions, you'll have multiple acquisitions or series, say a structural acquisition, a functional MRI acquisition, or a diffusion image. What Brainforge allows you to do is associate each one of those series with a different pipeline and set of parameters, and allows you to then you can queue them up and run them for every subject in your study. Now you can see for this analysis that we have, or for this study, we have VBM, voxel-based morphometry, which is a structural MRI analysis, queued up for all of the T1W 32-channel MPR 1 millimeter series. And then below that, you're able to see the total number of sessions that have been completed. And on each line below that gives you another subject and session. So you can see that, say for the top subject, that analysis has been set up but not run. The next one below had an error, and the one below that was completed. Then you can see the total number of completed, 107 out of 261. We also support BIDS, which is the dominant standard for dominant dataset specification for neuroimaging data. And here's an overview of all the processing we do. We can do VBM, we can do functional MRI using 2 different libraries. We can do arterial spin labeling, diffusion tensor imaging, and diffusion kurtosis imaging using FSL, which is good for finding connectivity, connectivity between different regions of the brain. Then here's all the toolbox, or all the analyses we do with GIFT. That includes Group ICA, DFNC, and Mancova. Also FreeSurfer and general linear models using SPM. Here's an overview of voxel-based morphometry. You can see the images at different steps of processing and in different tissue types. Here's fMRI pre-processing. You can see the mean image at various states of pre-processing. We also do FreeSurfer, which does a parcellation of the brain and can do a regression analysis across many subjects after the initial pre-processing is done. Here's arterial spin labeling, which also shows you a 3D view of the processing results. Here's diffusion tensor imaging, which shows you movement correction over time and the fractional anisotropy images registered to a standard space. Do the GIFT analyses, including 17 variants of group-independent component analysis. GIFT is one of the 2 major Group ICA toolboxes in use today. Here's an example of Group ICA. Here's the montage plots, time courses, and spectra for each component. Here's SPM GLM. You can see the parts of the brain that are associated with a task, and the design matrix. In the future, we're going to do MRI QC and MEG pipeline, historical QA view, allow users to run their own analyses, and further develop our command line interface. We're also going to do Jupyter notebooks to let users do interactive analyses. Furthermore, we have a NeuralMark portal, which will allow people to do normative comparisons of their data against a reference data set of thousands of images. This includes a brain age calculation. And if you want to learn more, please contact me. Email me at ewerner@gsu.edu or find me on Twitter. Thank you very much. Bye.
Okay, great. Eric, I think I see you on. I don't know if you want to unmute yourself. There we go.
Hey, how's it going?
And encourage everybody. Hey, Eric. We've got a first question is the Trends Gateway based on any existing gateway platform framework, or did you guys write your own?
No, we just wrote our own from just software development libraries. So the backend is based on the Django, the backend is written with the Django REST framework, and the front end is written with React using the Ant UI framework. So no, we kind of wrote it from scratch to a large extent.
Okay. I'll ask one more quick question, and that's, you mentioned reproducibility is one of the important goals, and I heard you mention that you can share the data at any stage in the pipeline, but what about the actual containers that have the workflows? You know, if somebody wants to reproduce and look at those, are those shareable? You know, what happens when you update those? Can you talk a little bit about reproducibility of that aspect of it?
Yeah, sure. Okay, so for right now, the containers themselves are being held privately on Docker Hub. We're probably going to open source them and share them, but we haven't pulled the trigger on that yet. So yeah, for people who have used our service and who are paying customers, or who have just, I guess, sorry, the more accurately, people who have used people who are users who've run their data with our platform, we can share those containers with them, and then they can run them. They can see what's going on, introspect them, and whatnot. So in terms of like reproducibility and maintainability, it gets pretty, I guess, gets pretty hairy because what you have to do is, you know, you have to navigate your way through different versions, like patches, minor releases, and major releases that break past functionality. So every time you change the interface, right, you have to change the front end code and the back end code, and so you have to create like so you have to find a way to do that in a way that's you can maintain the old stuff in case people want to rerun it. And you also want to maintain the, and you want people to be able to select from different versions of an analysis. And so we're just kind of putting together the plans for that in a very like fine-grained way, and we'll be doing that soon. But currently we just don't have. We are still relatively new, so we're mostly we haven't really had that many revisions on our images that run the analyses.
Okay, great. Well, thank you. Hopefully you'll stick around for the general Q&A, but let's move on to our third presentation, which is enabling secure and effective biomedical data sharing through cyber infrastructure gateways. This is another recorded presentation by Tyler Phillips, and I know both Tyler and Shreya Goyal are on to answer questions at the end. So Mike, please play the video.
Hi, I'm Tyler Phillips, and I'm here presenting with Shreya Goyal, and we're going over our paper enabling secure and effective biomedical data sharing through cyber infrastructure gateways. And we're from IUPUI, or Indiana University, Purdue University, Indianapolis, and Indianapolis, Indiana. So first, I'll go over the motivation and introduce our project. So the motivation of our project. So we have this Jetstream cloud computing service funded by the NSF, and it's widely used by Indiana healthcare researchers to enhance collaborative research. So the type of data that they're dealing with there is, you know, healthcare data related to like policemen and firefighters in the Indianapolis area. So although it's widely used, the Jetstream security features do not satisfy the requirements involving sensitive healthcare data and protected health information. So this drives the need and motivation for securing the cyber infrastructures that Jetstream uses through an easy-to-use, extensible, and robust cybersecurity architecture that can protect sensitive information being shared, for these scientific collaborations. So here I'll turn it over to Shreya to give us the introduction.
Okay, so the aim of the Dinosaur project is to develop integrated and trustworthy holistic secure workflow protection architecture that for cyber infrastructure such as Jetstream. The proposed cybersecurity architecture supports role and data hierarchies, as well as the dynamic changes of role and hierarchical relations within the scientific infrastructure. So now we'll provide an overview of our project. So currently, Dinosaur works on OpenMRS. OpenMRS is a community-developed open-source electronic medical record framework that is used for exchanging healthcare information. So this system is based on open standards such as HL7 for achieving interoperability with other systems while transferring or exchanging patient data. So as mentioned, currently Dinosaur project works with the OpenMRS database, but however in the future this can be applied to other databases. So the project runs on an OpenMRS image that is a template of virtual machine with pre-configured security techniques in it that will allow the users to securely access information stored in this database.
So in order to address our motivation of securing this OpenMRS image and allowing researchers to use it, we add some security components into the image, which then researchers can deploy through the Jetstream tool. So some of the security components we embed into the OpenMRS image here is biometric capsule-based privacy-preserving facial authentication, which we'll see, but it also includes two-factor authentication. We include dual-level key management, which is a cryptography-based hierarchical access control model. And we include secure digital provenance. So I'll go over each of these in detail later in the presentation. But again, these are the security components we're baking into the OpenMRS image.
Okay, so as mentioned earlier, Jetstream is a cloud computing environment that is supported by NSF for collaborative research. So it is designed to allow the researchers to get access to various computing and data analysis resources. So Jetstream allows the user to get access to virtual machine images pre-configured with an operating system and software that allows to do scientific computations in domain-specific tasks. So OpenMRS image will be built with all the security features and components implemented in it, so that when users will deploy a VM with our image, it will allow the users to remotely access and share sensitive data information to perform their research. So these are some of the steps on how we can deploy a Jetstream VM using OpenMRS image. So first of all, you need to create your Exceed account. So once you create that, so it will ask you to enter your username and password. And once you are authenticated, you'll see this Jetstream dashboard that allows you to launch a new instance of VM. So there you can click on the images options and then type our image, that is OpenMRS, and you'll see the OpenMRS base image. The latest version is 1.3, and then you can hit on the launch button that will allow you to deploy a VM with this image.
So now that we know, the overall architecture of the project, I'll talk about some of the security components that we're adding into the OpenMRS image that will allow researchers to collaborate, more easily and securely. So the first aspect is, in the current OpenMRS image, the only authentication method or scheme that you're allowed to use is regular username, password, login. But here we've added facial authentication. So due to the proliferation of biometric sensors and smart devices, biometric authentication has recently emerged as a promising solution to the loss, theft, and usability issue facing traditional authentication methods. So we talked to some nurses and healthcare professionals in the Indianapolis area, and they said that within this OpenMRS image, it'd be much more helpful to have biometric authentication, which is more useful for them on the job. But one issue facing, biometric authentication is that, if your biometric template or, facial attributes are stolen, the feature vector which represents that, it's a lot hard to cancel and reset that compared to how you would a password. So we need to secure those biometric templates used for the facial authentication. And that's where this biometric capsule scheme from 2019 comes in. How it works is it fuses the biometrics, or that feature vector of the user, with a reference subject in order to conceal the user's biometrics. So if you look at the bottom here, this workflow, you'll notice that, you have the typical biometric pipeline here. You take a user signal, by taking a picture of them, you sample and pre-process that image, you extract features, and then you perform some classification. But you'll notice in the biometric pipeline here, it also includes that reference subject, or RS, workflow. So each user is assigned an RS, and each time the biometrics are sampled and used for authentication, the biometrics are fused with the biometrics of that reference subject to conceal that user's biometrics. So there's a few advantages of this. One, we can just make the RS determined based on the user's role within the organization. So then at authentication time, a user needs to only provide their username, provide their role within the organization to determine the RS, and then allow the picture to be taken to provide the facial biometrics to the system. And it should be noted, although we're using the secure facial authentication scheme here by fusing the biometrics, we still are able to leverage state-of-the-art deep learning technologies during this facial authentication. So if we think about next moving on to access control, data access control, or operation access control, with the sensitive healthcare data. In the existing scheme and in many, healthcare domains, organizations typically set up their access control policies, which users have access to which corresponding data based on a role-based access control model. So the role-based access control model is pretty straightforward. You just define which users have access to which data. But unfortunately, there's no security component that's baked into that role-based access control model. So there's nothing to, enforce your access control policies. So that's why we've upgraded the OpenMRS access control model to a cryptography-based access control model, where there's cryptographic keys given to each user or set of group of users, like nurses and doctors, to actually explicitly enforce those access control policies which we define. And it raises a few key issues, such as hierarchical model design, how to generate that model, how to manage those cryptographic keys. So we use this 2019 IEEE TPS paper to carry that out. And what that ends up being, from the user's perspective in an OpenMRS image, is that some manager or admin within a hospital organization using this OpenMRS image can perform a user-friendly or generate a user-friendly definition of different roles and the data object privileges to the left here, and then we have a model generation algorithm which automatically generates all the keys to generate that access control model and enforce those access policies which we define. So the last part of this, which is still ongoing, is we're adding a secure digital provenance component into the OpenMRS image. So this is based on a 2014 paper, and what this is sort of similar to is blockchain technology, if you're familiar with that. So users utilize several cryptographic primitives, including cryptographic hash functions, private public key cryptography schemes, and digital signatures in order to generate a hash chain. So what this hash chain does is it records the ownership of a digital object, that digital object's current state, and any modifications performed upon that digital object, as well as when a user is trying to access that digital object. So this will be valuable to integrate into the database component of the OpenMRS image, and this is an ongoing work, as I mentioned.
Okay, so next is a usability experiment. So once the BioCapsule authentication system was implemented, we did a usability testing to see how it works. So we asked the students from privacy and security course to perform some of the tasks which is mentioned in the next slide, and then send out a survey to them to answer questions regarding the 3 authentication methods used. So these were the tasks that the students were asked to perform. First is like logging into OpenMRS using 3 different authentication methods, that is the biometric facial authentication, single sign-on, and the username and password method. And then they were asked to perform some of this basic tasks like creating patient records and then logging in as provider, as patient with different access and all those things. Then these were the 5 variables on which the questions were based and asked, that is the efficiency and effectiveness, satisfaction, preference, concerns, and confidence for the 3 authentication methods. So once we got the results, we developed a formative partial least square structural equation modeling to measure the relationship between the usability and security. So from the results, it was found that the biocapsule facial authentication was the most preferred, usable, and secure among the 3 authentication methods used. So this concludes that the Dinosaur project allows to build a secure, holistic, multi-layer protecting cybersecurity architecture that can be ported to multiple virtual machines on Jetstream. It allows for scientific data so that researchers and students can remotely access and share protected data in a convenient yet finely controlled manner. Thank you.
Thank you.
Okay, well great. So I know both Tyler and Shreya are on, so feel free to unmute yourself, and anybody has any questions, you put them in group chat. I'll start by saying I think it's super cool that you all are reporting, actually you did, and reporting on a usability study, because I think that's one of the things that in the community we don't talk about enough, and I know we don't perform them enough, because that's really important, the end usability. So I guess I'll just tee it up as to, is there anything else you want to say about the usability study? I don't know, maybe did you look at any type of digital accessibility type aspects of it or anything like that?
Yeah, so I think the main motivation is to give researchers some more flexibility in terms of the security components that they're using, if they're using this OpenMRS image in the research. So we can add all the security components under the sun, but at the end of the day it needs to be usable. So we have a couple different experiments underway, primarily led by Shreya here, but they're just getting feedback from students, and these students are both, taking our security courses at our university, as well as students studying, more things more on the healthcare side of things, so we can get both of those perspectives. So the advantage of the biometric, authentication that we found is, once you get it's kind of cumbersome at first, getting it all registered in the system with your face and stuff. But once you get past that initial point, a lot of people prefer that to the username and password, because, most phones and smart devices nowadays have the, the biometric sensor or embedded camera, in them. So, you have that flexibility to use that in a version of the image.
Great. We do have another question in chat, and it is the data actually in the VM along with the tools?
So at this stage, we're just using fake data, just to make sure all the tools are in place. But we're on the last year of this NSF CI/CI project. So now we're moving on to this more experimental phase past development, where we're getting this usability feedback, and that is part of our plan over the next final year of this project is to start trying to integrate real data and see how our intended audience, these researchers, to receive our final product here.
Okay. Well, I want to open it up now to kind of just a general Q&A for everybody. So thank you for that, Tyler. And I guess again, if anybody has any questions, feel free to drop them into the chat. But I want to start with, I think as I was listening to all 3 presentations, you all had comments in some form or fashion about how the target communities are not naturally inclined to using computational tools or using, these types of resources. So I'd like to start with saying, if they're not naturally inclined, what do you do for awareness? Just to, how do you make your target community aware of these tools and the fact that they can, do their jobs better, faster, quicker, whatever, as a result of this? So why don't we, absent anybody jumping in, why don't we just kind of go down in order? I see Rob, you're smirking, so I'm going to pick on you to answer first.
Sure. So luckily we had a target community, at least the target for the portal of the researchers, the medicinal chemists and the structural biologists who had an idea of what they needed to do drug discovery. They had done it before in the past. And they came to us relatively quickly after reviewing and said, hey, this is not what we're used to working in. We're going to need you to integrate with something else. And they brought the product that they were comfortable with to the project. And we, had it in the budget to do that. So it was not too bad. Now, the open access data sharing portal is, again, still being developed, and how people use that, I think, is one of the things we're doing there is both providing a place to pull the data and pushing the data out to places that the community is familiar with already, right? So they may not be familiar with what we develop as the OADS, but they may already be using the AMP-AD knowledge portal or synapse.org or something like that. So part of that is just putting it where they're used to, so they don't have to learn another system. And I think that's a advantage we have in OADS, is that we have other systems that the research community is used to using, and we should be able to create APIs to get that data to a familiar state that they're used to dealing with it.
Okay, Eric, anything you want to share or chime in on?
Anything I want to share? Maybe, let's see, do you have maybe if you could cue me with a more specific.
Well, how are you, I mean, you approach it from a variety of angles, but let's just do this. How are you marketing this? How are you communicating to the neuroimaging community about Brainforge and making them aware of the fact that it's there?
Oh, right. Yeah, so right now, a lot of our first customer is really ourselves. So we're running our own data on it, and we have contracts with other PIs and research centers to analyze their data. But we have so we used to just do all this manually, like with shell scripts and whatnot. So we created a web interface to make it more just to create more of an accounting trail, an audit trail or whatever, so you can see what happened, and also to run it more easily. So in terms of, really right now we're at like word of mouth. And I think part of the marketing really is just showing up to this conference, but also like writing papers, showing up to like conferences, things like that. We haven't really started a full-scale marketing campaign, but I think we're still somewhat in like beta mode, and I think once we feel like we're really solid, then we're going to get more heavily into marketing it.
Okay, great. Tyler, how about you all? Anything you want to share?
Yeah, I think so my professor, sort of the motivation with this is we've been consulting with some like interested parties here in the Indianapolis, Indiana area as we go here. And I think, for my part, my security privacy perspective here, you need to, make sure, especially in, the healthcare domain, that all the necessary, security and privacy components are there. But you also want to give the user the flexibility to fine tune things to their needs, So the access control component of our project is definitely that, as well as, the usability of the facial authentication.
Okay. Well, I'll do one more question, kind of round robin. I'm not seeing any other questions in the chat. You all talked an awful lot about the technical side of this, but I think, as we all know, particularly when you're dealing, and there were some questions here about PHI and HIPAA and things like that. But when you're dealing with any type of medical data, there's contractual regulatory type things as well. So just curious if anything in your experience of going through this really surprised you or jumped out, or any real big lessons learned on that side, not necessarily the technical side, but on the regulatory, legal, however you want to phrase it, side of what you're dealing with. So let's, Rob, go ahead.
Sure. So I think the thing that actually surprised me is that when we found out that I went into this thinking it was going to be clinical data from Alzheimer's disease patients, and so it would be subject to a lot of the HIPAA and PII restrictions, which it turns out that it wasn't. So I almost had the opposite. Rather than tightening, I had a loosening when I found out that it was only intellectual property issues. And so we were able to make that commercial connection a lot easier once we realized that there was no PII going off campus, right, or going to a cloud service. Now, as I said, it did become more complex even with the intellectual property in getting the lawyers involved and having them look through the data management plan. But the advantage here is that good data management plan made that process go much smoother than I think it would have without it.
Great. Eric, anything that surprised you on kind of the regulatory business requirement side?
Well, we have a lot of experience dealing with HIPAA data. So right now, one of the prerequisites for any data we accept is that it doesn't include any PHI. So we pull data from coins, which does hold PHI, but it's anonymized before we pull it. And then for other customers, we just tell them to anonymize it ahead of time. But I think we also have planned on our roadmap just a PHI flagging script or routine that will help us determine if there is some PHI, like in the headers and various files. It's possible to include PHI. So we'll sift through all those and warn someone if something does contain PHI. And then I think it's also important, we haven't had to deal with this yet, but it's good to consider that just to have like disclaimers on your website that say, this is not to be used as a clinical tool, just so you don't get in any trouble with the FDA or give anybody the wrong idea. And also, I think it's good to have disclaimers like, just that limit your legal liability a bit. Just say like, your data, we're not perfect. It's maybe possible that your data may get lost or something may happen. So, just be aware that this, that you take some risks by using our platform. I mean, you just have to, I think users should be aware of that.
Yeah. Make sure you don't claim to cure hair loss or something,
Yeah, exactly. Yeah.
Okay, and we'll give the final word to either Tyler or Shreya, whoever wants to speak. Anything that surprised you or lessons learned on your side?
During the development phase, we've been working with primarily like anonymized or fake data. So we haven't really run up against that yet. And also I've been pretty insulated from that because my professor and the professors working on this project have been, taking care of that. So, but yeah, before this project, this is my first project working kind of, even in the healthcare domain. I'm usually doing most of my work in the financial domain. So this is kind of, blown my mind seeing, everything that goes into, securing healthcare data, preserving people's privacy. So I've learned a lot through this project, but I don't know if I have any, specific comments on the, legal side or anything.
Okay. Well, we're at the end of the hour here, so thank you for all three of the presentations. This was really interesting. It is the last session of the day, so enjoy the rest of your day and evening or afternoon, depending on what time zone you're in. We will have the next plenary tomorrow. It's titled Usability, featuring Paul Parsons and Hiram, I'm going to get this wrong, Kirkendall, I think is how he pronounced his name. I know he was on here earlier. That's going to be at 1 p.m. Eastern, 10 a.m. Pacific tomorrow. So thank you again all. Feel free to jump into any of the other kind of social sessions or anything that's on Kiko Chat, and have a great rest of your day.